Hello. In this video we're going to take a look at the quantum harmonic oscillator, one of the most important problems in quantum mechanics. So here's the potential, written now in operator form as we're very familiar with that. But let's go back and write out the time-independent Schrödinger equation in terms of a wave function. So we have our kinetic energy operator and our potential energy here, and we see that it's just a quadratic potential. And we'll have an infinite tower of eigenfunctions labelled by integers n and a set of eigenenergies associated with them. So they're bound states and there's an infinite number of them. The potential looks like this, a quadratic, and drawing the states in fact we can guess roughly what they look like again from thinking about the infinite potential well and the finite potential well. And in fact the results that we're going to find look something like this. So we have a ground state wave function and it has a ground state energy. We're plotting again something like the real part at a particular instant in time. One of the most important features of the harmonic oscillator solution is that the energy levels are evenly spaced. I mean, I've drawn them very well, but the entire infinite ladder of energy levels is spaced evenly, and that's why it turns out to be so useful for all other cases. Also, in general, it's fairly similar to why Taylor series are so important to functions. While we may not be able to solve every set of possible equations that we might come across, it's often possible to pay attention to points near minima and maxima. Those are often the points we're interested in a particular problem, especially when there's potential involved. And around a maximum or a minimum, we can always expand the potential as the first order term being a quadratic. So the harmonic oscillator is often a very good approximation to questions of physical interest, but we can also solve it exactly and analytically. So it'll prove useful in a lot of other problems that you'll see later on in your career. So let's take a look in this video at solving it the old-fashioned way by using differential equations, and then we'll look at a much more elegant way using operators in a future video. So first, let's change variables slightly. We'll define alpha y equals x. Substituting that into the time-independent Schrödinger equation, we find this. And if we choose the following, alpha squared is h bar over m omega, we can rewrite the equation in the simpler form, where double prime here indicates partial derivatives with respect to y rather than x as it usually represents. So this is with respect to y, and epsilon n here is defined to be just a scaling of the energies En. Okay, so this is a fairly simple, a simple looking differential equation, an ordinary differential equation now, as y is the only variable in the problem. It's convenient to make the following substitution. So we'll switch from phi n of y to h n of y multiplied by e to the minus y squared over 2, so multiplying the Gaussian term. When we make the substitution, we find the equation here reduces to the following form, which, while not particularly much nicer than this one, was already known. So this was known before quantum mechanics, and it's called Hermite's equation, where I'm certain I'm pronouncing this person's name incorrectly. So it was known already. Often what you do when you're trying to solve differential equations analytically is simply massage them into a form where someone else has solved it hundreds of years ago, and this is no different. So the solutions hn of y are what are called Hermite polynomials, again almost certainly pronounced differently to that. So they look like this. So they're defined by this expression involving powers of the derivative, the total derivative with respect to y. The first few look like this, and so on, and you can work them out yourself. And these Hermite polynomials are eigenfunctions of that differential equation, Hermite's equation that we saw on the previous board, and the corresponding eigenvalues are as follows. That is, they're just the odd numbers. So there are a couple of important properties of these Hermite polynomials, which we'll look at now. So the first is that they are orthogonal to one another. That is, the inner product defined for functions of hm and hn is some prefactor multiplying the Kronecker delta, delta n m. So if n doesn't equal m, the inner product is 0. If n equals m, it's 1 multiplied by a normalization factor. The only major difference here is this object here, and this is what's called the weight function. So in general, the inner product between two functions can have a weight function like this. This happens to be useful in many cases, and in this case the weight function happens to be a Gaussian. So this is all worked out by Hermite and others a long time ago. Another important property of these Hermite functions is that they form a complete basis. So the Hermite polynomials form a complete orthogonal basis for functions f of x satisfying this property. But actually we knew this from our postulates of quantum mechanics. It's an orthogonal basis rather than orthonormal, just because the normalization is a bit off here. We'll substitute back in to solve the full quantum problem in a second, and then we'll have a complete orthonormal basis. But this is one of our postulates, so the fact that it's solving a quantum problem tells us that this should be true. And this condition down here just tells us that the functions we're considering must be normalizable in this sense. But again, we knew that because our functions should be living in a Hilbert space, and part of that definition is that they're square integrable, so that they give normalizable wave functions. Okay, so let's substitute it back in to look at the solution to the harmonic oscillator. So the energies, as promised, are evenly spaced in energy. You'll notice that the ground state has n equals 0, but it does not have 0 energy. So there's what's called a ground state energy of this system. The minimum energy a particle can have in this quadratic potential is not 0, it's h bar omega over 2. This is also sometimes called a 0-point energy for the system. It's somewhat mysterious, but not too much of a problem. If you think about it, the potential energy of something, you can increase all the potential energies in the universe by the same amount, and that wouldn't be an observable effect. So we have methods of dealing with this when it comes up in other problems. The solutions, the eigenfunctions, take the form of Hermite polynomials being multiplied by some of the bits and pieces. These now form a complete orthonormal basis. And more generally, if we look at the equation itself, for the time-independent Schrödinger equation here, it reminds us that, well, we've just put this potential in, a quadratic potential. What we're really looking at here is the quantum version of a spring oscillating, which would be described by a potential like this, or any of the set of problems which we approximate as being like that. So, for example, a pendulum swinging at small angles. But again, we use it quite ubiquitously. The reason the spring is such an important problem in classical mechanics is, again, that we can approximate many functions by the quadratic points, the relevant bits of interest at the maxima and minima. Okay, so in the next video we'll take a look at solving this again using a different method based on operators. Thanks for your time.